Okay, Assalamualaikum and hi. We are from Group 5 and we are presenting about our project title, Vehicle Braking Analysis for Engineering Mathematics 1. My name is Adri bin Muhammad Fuad, matrix number BC254226.
Hi, my name is Naufal Hakimi and my matrix number is BC252996.
Hello, my name is Sabanesh bin Sedibijam and my matrix number is BC251619.
Hello, my name is Mohammed Abdurrahman Sheikh and my metric number is BC255128.
Okay, moving on to the first slide. Okay, this slide introduces us to our project, which is vehicle braking analysis using engineering mathematics concepts. First, braking is important because it affects road safety, crash avoidance, and safe stopping distance. A vehicle must be able to slow down and stop safely to prevent accidents. Next, the problem we are studying is that vehicles must stop safely after braking, and the stopping process depends on speed, time, and distance. This project, we analyze two main things: braking time, which is how long the vehicle takes to stop, and braking distance, which is how far the vehicle travels before stopping. Finally, mathematics is needed to predict stopping behavior because to help design safer vehicles and roads. So, by using engineering mathematics concept, we can understand and model how vehicles slow down in real situations.
Mathematics makes braking predictable. So by using functions, differentiation, and integration, we can actually model exactly how a car stops. To keep our calculation simple, our model relies on a few key assumptions, which is that the car travels in a straight line on a flat road, and that the car slows down at a constant rate, and lastly, we are not including air resistance or the driver's reaction time. By stripping away these variables, we can use calculus to turn a moving vehicle into a predictable mathematical equation.
So, here are a sample problem. Let's take a vehicle is moving with a velocity of 200 meter per second. Sorry, to 20 meter per second initially. Then the brake is applied, causing the vehicle to slow down with a constant deceleration of 5 meter per second square until it comes to rest, reaching velocity of 0 meter per second. So this is the mathematical approach. First, we have to find the velocity function. As you can see, acceleration is the rate of change of velocity in respect to time. So we can write acceleration as dv dt. And we know that the car decelerates with a constant speed of 5 meter per second square. So we can write dv dt is equal to -5. And then we use integration. Integration is a mathematical process that reverse differentiation. So just now we have acceleration. So the reverse of acceleration is the velocity. So we integrate -5, and then we get -5t plus c, which is the constants. Now this is the -5t plus c is a velocity function, but we can find the c by substituting the initial velocity of the car. So the initial velocity of the car is 20 meter per second. So we substitute it into the equation, and then we got c is equal to 20. So we substitute the 20 back into the original equation. Therefore, we got the velocity function is equal to vt is equal to -5t plus 20.
Now for calculating braking time, the vehicle is at rest when the velocity, or v, is equal to 0. So using the velocity function, we are going to substitute the v of t, which is 0, and then we are going to divide by -5, or divide by 5 to isolate the t, which gives us a time of 4 seconds.
I will now demonstrate how we found the distance function. So the purpose of finding the distance function is so that we can find the braking distance. So basically, we take the velocity function that we found earlier and we integrate it to find the distance function. So basically, the workflow is that you take the acceleration function, integrate it, you find the velocity function, and then you integrate the velocity function and you will find the distance function. Okay, so we integrate it with respect to t, and then we'll get -2.5 t squared plus 20t plus c. And now we need to find the constant integration constant. So how do we do it? We use the initial condition, which is s at time t at t equals 0, and we use this value because that is just before the car starts to brake. And then we will find that c equals 0, and then we find the distance function, which is negative 2.5 t squared plus 20 t.
Now we want to find the braking distance. As we know, the time taking for the vehicle to completely stop is 4 seconds. We have distance function. So now we substitute the t equals to 4 seconds, which gives us the result of distance is 40 meter. Next. So now for the discussion. From the calculation, the vehicle braking behavior under a constant deceleration of 5 meter per second square and initial speed of 20 meter per second was determined. The analysis tells us that the vehicle stopped in 4 seconds and traveled 40 meters while braking. This has several practical implications. First of all, speed is matters. Higher speed will increase both stopping time and distance, emphasizing the need for speed control. Second is brake performance. Vehicle with stronger braking system stop faster and cover less distance, which is important for safety. And then road and traffic design. Knowing typical stopping distance help engineer plan safe intersection, traffic signal, and road layouts. Lastly, predictability. Mathematical model like this allow engineer to estimate how vehicle behave under different conditions, aiding in safety planning and accident prevention. In short, this result not only shows the stopping performance, but also provide valuable insight for vehicle safety, braking system design, and traffic management.
In conclusion, using a simple mathematical model, we analyze how a car slows down while braking. We assume ideal conditions like constant deceleration to make calculations easier. Functions allow us to describe how a vehicle's speed and distance change over time. Differentiation helps us understand how the speed decreases during braking by showing how velocity changes with time. Integration is then used to find how far the vehicle travels while slowing down by calculating the distance from the changing speed until the vehicle comes to a stop. So an inference we can make from our braking model that is the ideal conditions that the only factors that affect the distinctness of the velocity function, and consequently the distance function, braking time, and braking distance are the initial velocity and value of deceleration. So basically what I'm saying is that when someone calculates like braking distance and braking time using our model, um, for for uh, for distinct cases, the only thing that affects, as I said, the velocity functions, the functions, and the braking time and the braking distance that you'll find are the values of the initial velocity and deceleration that are in question. And then another inference that we can make from our calculations is that higher initial speed increases stopping time and distance, and that higher value of deceleration reduces both stopping time and distance.
That's all from us. Thank you.